Hi friends, in our last lecture we have discussed combined gas equation. From that we have obtained characteristic gas equation and ideal gas equation, and even we have seen numerical based on that topic. Now in today's session we will be discussing relationship between Cp and Cv, that is specific heat capacity at constant pressure and specific heat capacity at constant volume. So this is Faizan Kagdi and I welcome you all to our lecture series of Basic Mechanical Engineering. So let's start with our topic, relationship between Cp and Cv. That is, basically we need to derive Cp minus Cv is equal to R. Now the first question comes that why a gas has two values of specific heat capacity, that is one at constant pressure, another at constant volume. So this first of all we need to understand, and after understanding we are going to decide that which value is greater, that is Cp is greater or Cv is greater. So first of all let's quickly revise the definition of specific heat capacity. We know that specific heat capacity is the amount of heat energy required to raise the temperature of 1 kg of a gas by 1 degree, that is either 1 degree Celsius or 1 Kelvin. So in order to do that, whatever heat energy is supplied, that heat energy is called specific heat capacity. Now the next question on the spot comes that why a particular gas, let's say we take an example of an oxygen. So oxygen gas has a specific heat capacity at constant pressure as well as at a constant volume. So why it is so? So in order to understand this, I have shown a two piston cylinder diagrams. That is, in first case I am supplying heat energy to a gas at constant volume. In the second case, I am supplying heat energy to a gas at constant pressure. So let's understand this. In case of a constant volume, as our target is to maintain a constant volume of a gas, so on the top of a piston, I have placed a stopper, which means a stopper is not going to allow a piston to move in an upward direction. That is, in short, it is not going to allow a displacement of a piston, which means we can maintain constant volume. Now since it is our closed system, so we can apply our first law of thermodynamics, that is Q is equal to delta U plus W. Now I have taken an example that let's say I am supplying 1 kilojoule of heat energy at constant volume to a gas, that is 1 kg gas, which is at 25 degrees Celsius temperature, and let's assume that this 1 kilojoule heat energy has increased the temperature of this gas from 25 degrees Celsius to 26 degrees Celsius, which means what? That this 1 kilojoule heat energy is a specific heat capacity of this gas at constant volume. Now why I can say that? So as we know that according to first law, whatever heat is supplied will be totally converted into internal energy. That is, that heat energy will increase the temperature of a gas. Okay. Now when a same 1 kilojoule heat energy is applied to a same gas, but in a second case heat is supplied at constant pressure, along with that we are allowing a piston to perform a displacement, that is, it is going to move from state 1 to state 2. So what is going to happen? So when a first law is applied in this case, that is Q is equal to delta U plus W, then that 1 kilojoule heat energy is divided into two parts, is split into two parts. The first part is that it is going to do a work output, that is, a piston is going to perform a displacement. Okay, and second part is converted into internal energy, that is, it is going to increase the temperature of a gas. Hence we can say that 1 kilojoule heat energy, which is a specific heat capacity for a particular gas at constant volume, is not a specific heat capacity at constant pressure, as some portion of it is converted into work output. So it is very obvious that let's say that in order to increase the temperature of a gas at constant pressure from 25 degrees Celsius to 26 degrees Celsius, I have to provide more heat energy compared to 1 kilojoule. Let's say that by providing 2 kilojoule heat energy at constant pressure, the temperature of a gas is increased from 25 degrees to 26 degrees Celsius. So now I can say that this 2 kilojoule heat energy is a specific heat capacity at constant pressure for the same gas. Hence, the gas or any type of a gas will always have two values of specific heat capacity, one at constant pressure and another at constant volume, and it is very obvious that Cp will always be greater than Cv. So the next term is adiabatic index gamma. So the ratio of Cp to Cv, that is Cp by Cv, is called adiabatic index, and it is all denoted by gamma. Okay, now for air we have a value of Cp which you need to keep in mind. Cp is equal to 1.005 kilojoule per kg Kelvin, and Cv is 0.7175 kilojoule per kg Kelvin. Now for air, adiabatic index gamma is equal to Cp by Cv, which will be equal to 1.005 upon 0.7175, which will come 1.4. So the value of adiabatic index gamma will be different for different gases, as the value of Cp and Cv will be different for different gas. Now let's start to determine a relationship between Cp and Cv. Now we need to consider two cases. In case 1, we are going to supply heat energy to a gas keeping volume constant. Okay. So what is the formula of heat transfer at constant volume? So we know the formula of heat energy. Q is equal to mc delta T. Okay. So let's consider a gas has a mass of 1 kg and it is heated from its initial temperature T1 to its final temperature T2. So heat transfer according to mc delta T will be equal to Qv is equal to mcv T2 minus T1. Okay, so this is a heat supplied at constant volume. Now second, how much work can be obtained when heat is supplied at constant volume? So we know that when a volume is constant, so piston is not going to move, and if there is no displacement, then there will be no work output. So we can say that work done is equal to PdV, pressure into change in volume. So its integration from state 1 to state 2, that is V1 to V2, PdV will always be equal to 0, as there will be no displacement of a piston. Okay, so from this we can say that according to first law, Q is equal to delta U plus W. So whatever heat energy is supplied is totally converted into internal energy. So delta U is equal to QB, which is equal to mcv T2 minus T1. So these are the equations which we have obtained from case 1 in order to find out. This is the first step to form a relationship. Now consider the second case in which we are going to supply heat energy at constant pressure. So the formula is going to remain same, that is Q is equal to mc delta T. Now what will be the change? The only change will be in Cp. In place of C we are going to place Cp. So the formula for heat supplement at constant pressure Qp is equal to mcp T2 minus T1, that is final temperature minus initial temperature. Now in this case we are going to say that piston is going to perform a displacement, that is going to move from state 1 to state 2. So work output will be obtained in this case. So let's find out the work output. Now we know the formula of work output, that is W is equal to PdV. Okay, so applying a limits from state 1 to state 2, we can write work done is equal to P V2 minus V1. Okay, and the internal energy that can be increased will be delta U is equal to mcv T2 minus T1. Now our next target is to combine the equation from case 1 and case 2. Okay, so from case 1 we are going to take internal energy, that is delta U is equal to mcv T2 minus T1, and from case 2 we are going to take heat transfer, that is Qp, and work done, that is P V2 minus V1. As we are very clear that we need to combine two cases in order to find out a relationship between Cp and Cv. So for doing this, we are going to use the first law of thermodynamics, that is Qp is equal to W plus delta U. So as we have determined heat transfer at constant pressure, Qp is mcp T2 minus T1, and work done which we have found out at constant pressure will be P V2 minus V1. So mcp T2 minus T1 is equal to P V2 minus V1 plus delta U. So delta U, that is a maximum internal energy of a gas that can be increased, which was obtained at constant volume. So I have taken it is equal to mcv T2 minus T1 in order to combine these two cases. Okay, so in the next step I have written mCp T2 minus T1 is equal to, I have converted P V2 minus V1 into mR T2 minus T1, as we know the our characteristic gas equation, that is Pv is equal to mRT. So from that I have written Pv2 is equal to mRT2. Now taking mR common out, so the equation can be written as mR T2 minus T1 plus mCv T2 minus T1. Now further, from both the sides we can cancel out mass into T2 minus T1, m into T2 minus T1. So what will be the final equation? So it is going to become Cp is equal to R plus Cv, and so finally we can write Cp minus Cv is equal to R. So this is the relationship between specific capacity at constant pressure and constant volume, which is equal to our characteristic gas constant capital R. And since this equation was derived by Mayer's, this equation is also called as a Mayer's equation. Now let's simplify this equation further. So in our next step, as you can see on your screen, that I have divided the equation by Cv on both the sides. So what we can obtain? We are further simplifying the equation. Okay, so we can obtain Cp by Cv minus 1 is equal to R upon Cv. Now we know Cp by Cv is our adiabatic index gamma, right? So I have written gamma minus 1 is equal to R by Cv. Now finally our equation that can be obtained is Cv is equal to R upon gamma minus 1. So what is the use of this equation? So whenever in our numerical, if R and gamma is given in a data, then by using that value we can determine a value of Cv, and once Cv is obtained, then we can determine a value of Cp by using our Mayer's equation, that is Cp minus Cv is equal to R. Okay, so now you have to keep in mind the equation of delta U which we have obtained during this solution is delta U is equal to mCv T2 minus T1. Similarly, we can determine change in enthalpy, that is delta H. So we know the formula, delta H is equal to final enthalpy minus initial enthalpy, that is H2 minus H1. Now we know the formula of enthalpy H, that is U plus PV, right? So at state 2 I have written U2 plus P2V2 minus at state 1, that is U1 plus P1 V1. Arranging the terms, we can write U2 minus U1 plus P2V2 minus P1 V1. Now U2 minus U1 is basically a change in internal energy, that is delta U, which we have obtained, that is mCv T2 minus T1. So I have substituted that value mCv T2 minus T1 plus I can write PV in form of mRT by using characteristic gas equation, right? So in place of P2V2 I have written mRT2, in place of P1V1 mRT1. Now further, in our next step, I have placed a value of R, that is from Mayer's equation R is equal to Cp minus Cv. So we can write the equation mCv T2 minus T1 plus m Cp minus Cv in a bracket T2 minus T1. So after expanding this term, if you see carefully, the term mCv T2 minus T1 from a first side and a term minus mCv T2 minus T1 are going to get cancelled out. So what will be remaining? So we would say mCp T2 minus T1 will be remaining. That is our final answer of delta H. So from this we have also got another formula, that is for change in enthalpy, which is equal to mCp T2 minus T1. Okay guys, so we are keeping up till here. I hope that you are clear with this topic of relationship between Cp and Cv, that is Mayer's equation. In our next session, we will do numerical based on this topic. Till then, stay tuned and thank you all.